Welcome everyone, and thank you. Today I'm going to talk about digital identity risk assessment with Neo4j. This talk is actually based about an actual product we developed here in Accenture Lab. So everything is going to be real. This is nothing theory. This is actually a thing we are going to use inside of Accenture. So to start, a little bit about me. My name is Daniel Nachmias. I'm from Israel. I hold a master's degree in information and software system engineering from Ben-Gurion University. Throughout the academia, I focused on applying machine learning and deep learning solutions for various cybersecurity use cases. Industry-wise, I worked as a data and applied scientist for more than 6 years. In different industries, including Deutsche Telekom, IBM, Nike. And today I'm an applied scientist at Accenture Cyber Labs in Israel. Feel free to connect on LinkedIn if you wish. To start, we want to start with a moment of silence. As you all know, on October 7th, my country suffered the most horrific terrorist attack since 9/11, more than 1,400 Israelis killed and more than 200 kidnapped and held hostage. Let's start with a moment of silence for those affected, and our hope and prayer that the hostage will come home back soon. Okay. So we start with a common phrase that we hear very often from graph enthusiasts is that graphs are everywhere. While this is true, this is only true in theory. Okay, graphs don't just present themselves. The message is that we need to actually invest very significant R&D time to create them. Graphs are present in various domains and represent connections and relationships between entities, whether it's social network, transportation systems, or biological interactions. Constructing graphs, however, can be challenging. Data is often spread across different systems and formats. The process of bringing together scattered data to form a coherent graph requires a tremendous R&D effort. However, if we do invest in gathering data into a knowledge graph, we open new opportunities to effectively leverage data science. The structured nature of a graph enables more efficient analysis, discovery of patterns, and extractions of valuable insights. But what makes a graph a knowledge graph in contrast to just a regular graph? A knowledge graph assigns meaning to entities, relationships, and attributes using ontologies. Ontologies are basically the schema that graph database coheres to. This means that it goes beyond just organizing data structurally. It strives to capture the semantics of the information, allowing for a rich contextual representation of knowledge. An ontology-driven graph ensures semantic consistency in data representation. This supports advanced querying and reasoning capabilities, which can then be translated to valuable analytics and features that support existing machine learning pipelines. In this talk, I'm going to focus on a knowledge graph that describes the digital identities within the organization. But first, what are digital identities? Digital identities store personal and professional data, access credentials, roles, and permission that describes some identity inside an organization. They enable secure and personalized interaction within the organization, within the organizational digital systems and resources. By examining the interaction with each other and corporate resources, we can establish a comprehensive knowledge graph. And this is exactly what we did in a minute. This knowledge graph offers valuable insights into risks associated with identities and how these risks propagate across the organization or can propagate across the organization. This enhances our capability to proactively manage and mitigate potential threats. So, as I said, this presentation focuses on our experiences in developing Identity Trust Engine, or ITE in short, a solution built upon a knowledge graph that empowers us to evaluate and prioritize risk associated with digital identities within our organization. To build this solution, we extracted data from disparate systems and curated a cohesive, well-defined knowledge graph. This allows us to leverage graph data science to assess and prioritize mitigation of risk among the organizational digital identities. So data regarding digital identities is distributed across multiple commonly used systems within the organization. For example, HR systems store information about the identity's position in the organizational structure. SIEM systems capture data related to security events linked to the identity. And identity access management systems offers insight into the identity's access permission for corporate resources. By creating a mapper that consolidates and associates each data point with its corresponding identity, we can establish a knowledge graph that effectively constructs a digital twin of the digital identities within the organization's digital ecosystem. After completing this process, which I described earlier, we established a comprehensive knowledge graph that represents our digital identities ecosystem, or we can also say a digital twin of the entire organization. This knowledge graph consists of an ontology, demonstrating the structure and components of the graph. Here you can see an example of such ontology. It is crucial to maintain clear and consistent semantic meaning for the labels assigned to the nodes and relationships within the graph, as this plays a pivotal role in facilitating accurate and meaningful analytic process. So actually, when we run algorithms, we have to specify labels and nodes that participate in the algorithmic process. And to do so, we must have a consistent and coherent ontology. So I'll describe a few algorithms we developed on our own that helps us unlock hidden features that can boost our existing machine learning pipelines that we weren't able to do if we weren't using a knowledge graph. So, for example, is risk propagation. We know that we have data that comes from the SIEM that quantified security events and give us quantified risk about a digital identity. Now, we also have information of which corporate resource the digital identity interacts with. Once we have all this information, we can actually simulate or try to predict how much of a risk will propagate among the digital identities through this connection. Okay, so let's give a quick example. Okay, let's give a quick example. For example, I want to propagate risk between identities and corporate resources. That can be workstation, application, or just whatever. We already have the entitlements that each identity has to every resource. And we can propagate risks in such a manner that once we have a bipartite graph that describes these connections, we can propagate risk from one side to the other. So according to any function, for this simplistic example, we will use a max function. And for example, this first identity will have the maximum between 0, its own risk, and the risk associated with its neighbor, which is 4, so it will get the value of 4. This identity will have the maximum between 5, its own risk, and 4 and 7, so it will get the value of 7. And once we have that, we update the total risk of an identity accordingly, and then we can iterate to the other side. So this identity right here will get the value, the max value between 4, 4, and 7. Okay, and then we can go on until we reach a specific number of iterations, or until we reach convergence and we see that risk is not propagating anymore. Now we generated a new feature. This feature describes the implicit risk of a resource or identity that can be propagated via a risky entitlements. So just on implementation, it's pretty straightforward. However, we must implement this right here, the propagation query in Cypher. We as developers, we do not like to keep strings, okay, inside our code. And to do so, we have simple to the rescue. Simple is a package that was developed here inside of Accenture. It coheres to the string builder design pattern. It allows us basically to build Cypher queries in a Pythonic manner and avoid using strings. This makes implementation much more intuitive. So this is an example of the Cypher query that we want to implement, and this is how it is done in simple. Notice how I'm barely using actual strings. I just use the query builder to define the query, so match and then a node with some label related to another node with some label. So please, if you are using Cypher queries in Python, please try to work with simple. It will make your life much, much easier. Okay, so now I will have to end the session. I just like to point out that also, instead of implementing your own custom queries and analytics, it is very, very important to leverage GDS when you can. So it's a very simple and very powerful analytics package that I urge you to try. It can help you a lot. For example, we can use a PageRank to assess the organizational importance from the organizational structure inside a knowledge graph. This is an actual example that we use, and it's already implemented in GDS, and it's very, very powerful. Thank you, guys.